So it's, yeah, there we go. So thanks to Vanya and the speakers organizer helping to make this happen. So let's start off with our first speaker, number one in Sydney, Behrouz, where you go.
Sure. Yeah. Thanks so much. Thank you for the invitation, and thank you all for the organization of this thing. I know this is not easy, but so thank you for that. Okay, so the topic of my talk is basically sort of Birational geometry of smooth projective family of manifolds. Basically the main theme of this talk is how sort of a variation in algebraic or Birational structure in fibers of sort of smooth families impose rather strict conditions on what base of such families can be. So I'll start with an example, which is basically Shafrovich conjecture. And basically what this conjecture says is that over curves of this form, so if you have a smooth projective family of homogeneous curves, so the base is of dimension 1, fibers are of dimension 1. Now, if the base is one of these things, P1 elliptic curve, C or C star, then the conjecture says that the family should be isotrivial. So there shouldn't be any algebraic structure variation in this family. So this is what isotriviality means. They're just algebraically, they're all the same. Okay, so if I put this in other words in a different way, so in other words, what this says is, in other words, if the moment we have some variation in such a family, so let's say variation is not 0, then the base should be of log-John type. So the codary dimension of the base should be maximal. So, so this is what I was saying. This is the theme of having some variation in the family imposes strict conditions on the base. And these conditions are always in sort of some sense of sort of positivity of some line bundles. Okay, so now what I want to talk about here is higher dimensional generalizations of this conjecture. So by the way, I should say that this conjecture was already solved in the 80s. Now, what we want to do is sort of find candidates or talk about candidates for higher dimensional fibers. So if we are looking for such behavior, sort of connection between variation and positivity in the base of the canonical bundle, what sort of higher dimensional fibers do we need to choose? So I will talk about this, and I will start with a case where variation is maximal. So by variation being maximal, I mean variation in a family will be equal to the dimension of the base. So this sort of the first generalization, as far as I'm aware, is due to Vivek, where he basically replaced or sort of generalized the candidates for fibers to canonical polarized manifolds. So Vivek conjectured that if you have a sort of smooth projective family of manifolds whose fibers have ample canonical bundle, then the moment variation is maximal, then codary dimension of the base should be maximal. So in a way, you sort of translate the maximality of variation in the family to maximality of the codary dimension of the base. So basically he, in the Shafrovich conjecture, we have homogeneous fibers. So here, of course, for them, canonical example. So, having ample canonical bundle for the fibers seems to be a natural thing, to have a generalization of Shafrovich conjecture. So this was conjectured by Vivek and solved by combined work of Vivek Zhu and Compound Pong. So this is the situation in the, this is the sort of higher dimensional generalization when the variation is maximal. I should also say that we can talk about a much larger class of fibers in this context. So we can replace we can generalize the condition for the fibers to have ample canonical bundle to fibers having good normal models. So this was done, so later generalized, so this was later generalized. By Vivek Zhou in dimension 1 and Birational to fibers with good neural models. So projective families, manifolds with good neural models are basically our candidates for higher dimensional analogs of homogeneous curves in this context. Okay, so what about the non-isotrivial family case? So here, I assume that variation is maximal. What happens if variation is not zero? So what sort of generalization can we sort of expect for Shaffer-Rich type conjecture? So here, one conjecture is due to Kebekus-Kovács, and this is closely connected to a conjecture Campana. I will talk about the connection, but for now I will just talk about Kebekus-Kovács conjecture. So this conjecture says that whenever you have a non-isotrivial family of projective manifolds with good neural models, then you end up in either of these two cases. So either codary dimension of the base is non-negative, in which case codary dimension sort of is an upper bound for variation, or codary dimension is negative and variation cannot be maximal. So, so this is all sort of generalization of Vivek's conjecture as well. So when you have variation maximal, this conjecture recovers Vivek's conjecture. Okay, so these are the sort of generalization that we have, and I will talk about of Shaffer-Rich conjecture. And so I should say, so the main theorem is that this conjecture, Kebekus-Kovács conjecture, is true. So that's the main theorem, and I will sort of talk about all these things and the sort of general strategy of how one approaches these problems and how this theorem works roughly. Okay, so let me just start talking about general strategy. So how does one even sort of start approaching these problems? Okay, so let me again divide the two cases. So I will talk about maximum variation and then sort of more general non-isotrivial case separately. So in the maximum variation case, so first I should sort of fix some notation. So let me fix some notation. So I'm just going to choose a smooth compactification of my original family. So this is a smooth compactification. So these pairs, I'm assuming that these pairs are log smooth. Which is the sort of thing one can always do by going to hard birational model. So step one in sort of our approach to these problems, in the general approach to these problems, is Hashtaretic. It can also be done analytically, but I will talk about the Hashtaretic method. Okay, so the first thing is one can translate sort of this maximality of variation to a sort of positive sheaf inside the sheaf of plurilogic differential forms in the following sense. That assuming that we have maximal variation, there's always a line bundle inside the sheaf of plurilog differential forms in the base with maximal codary dimension, such that codary dimension of L is equal to dimension of the base. Or in other words, L is a big line bundle in the base. So there is, so I should say, for some sufficiently large natural number, we always have this. So this is sort of the mostly Hashtaretic results, and this is due to Vivek Zhou and Birational So in the maximum variation case, these are this was definitely known, and I should say, so this covers both cases. So this covers canonically polarized case, and more generally, Goodwill models. So whenever we have a smooth projective family manifolds with Goodwill models, one can always construct a line model like that inside the sheaf of plurilogic differential forms. So now the question is, okay, now that we know there is some positivity inside the sheaf of plurilogic differential forms, what can we say about positivity of the top, sort of the top forms? And this is a birational result. This is component-component result. So this is step 2, which says that whenever, you know, we have a big line bundle like this, then it follows that codary dimension is maximal. So in some sense, from bigness of the sheaf of plurilogic differential forms, you can go to bigness of the log canonical bundle. So this is the general approach. Always, in all these results, this is the general approach. There's a Hausch-Radek one or analytic one that gives us the first part, this line bundle, and there's a second part, which is birational. Also, there's also analytic proof actually about component as well, that sort of gives you this relation, bigness of pluridifferential forms to bigness of the log canonical bundle. Okay, now this was the maximal variation case. So what happens when variation is not maximal? So when variation is not maximal, the situation is slightly more complex. The first step is to find a reasonable model function associated with the family. And I will discuss what I mean by reasonable, but that's always the first step. So one likes to have a sort of a modular functor that is easy, you like to work with, or is easy to work with, that you can associate to the family that you start with. So that's one thing that we want to have. And the other thing that we want to have is use this modular functor to construct the line bundle that we saw in the max variation case at the level of model stacks. So here, in the non-isotrivial case, I will mostly focus on this step. So this is mostly sort of the Hausch-theoretic algebraic step. So I want to construct a subsheaf inside the plurally differential forms with the right amount of positivity. That's what I want to do. And for this, you kind of need these two things. So you have, once you have a good model functor, basically what happens is that you can sort of go to a place where variation is maximal and basically apply what you know about how to construct such sheaves in the maximal variation case. So this is what I mean by constructing at the level of model stack. So this is, I'll make this precise now. So what do I mean by this? So I mean, first of all, that if we start with a family, with a smooth family of projective manifolds with good models, then at the minimal level, there's always a reasonable model functor. So no matter what relative minimal model program you run, at the minimum level, there's always a meaningful good model functor. And it's reasonable in the following sense. So this model functor, by the way, so this notation. So this notation, I mean, U prime is minimal over V, and this L is polarization. So as a polarized family, there's a map to a reasonable modular space. That's what this notation means. So let me say what I mean by, I keep saying reasonable. Let me say what do I mean by that. So I mean that this coarse modular scheme. So let me just say that this modular functor has a quasi-projective coarse modular scheme. As a quasi-projective coarse modular scheme, which I will denote by just capital M. And then I just, another notation, we denote the induced modular map by mu. So this will be my induced modular map from the base of the family to this coarse modular scheme. So this is just a regular map. This is just a regular map. Okay, and another thing that I mean by sort of this modular functor being reasonable, this is what I mean. So I mean that variation in the family is exactly equal to dimension of the image of this modular map. So okay, so I've been very vague. I didn't actually define what variation is, and this is why. Because once we have those results, then I can easily talk about it. So whenever I'm talking about variation, I'm talking about the dimension of the image of this induced modular map. Okay, so now that we have this reasonable modular functor and this good, quasi-projective coarse model scheme, then I can sort of tell you what I mean by constructing this line model at the level of modular stack. So this is what I mean. So I mean that using this modular functor, I can sort of pull back this family to a new base over which I have maximum variation. So my original family is F. I can pull it back to Z, where the variation is now maximal because this is generically finite. So this is generically finite map to the coarse modular scheme. By the way, so I'm compactifying, so I should compactify that as well as a quasi-projective variety. So by 2, this means that the variation of this new family over Z, which is, by the way, generically finite over the coarse modular scheme, is maximal. So now I have a sort of family with maximal variation over Z. Okay, now I can construct the line bundle over Z. So this is what I meant by what I said by constructing line bundles at the level of model stacks. So we can construct a big line bundle, the big line bundle that we like, big line bundle, L, let me call it LZ on Z. So LZ is now inside the sheaf of Fourier log differential forms with, so dfz is the discriminant locus of fz. Some natural number, sufficiently large M. So now I have that. Okay, so by the way, so there are different sort of, as I kind of mentioned in the beginning, there are different ways of constructing these line bundles when you have maximal variation. There is, of course, the original method of Behrouz to construct them. There's a method of Cauchy using Hodge models to construct them. And sort of this method, so the method that I use here is slightly different from both. Of course, it's completely inspired by both of them, but it's different and is based on some sort of functorial properties of some filtration that you have for relatively round complexes. I will mention what I mean by that, but I just want to say that this difference is actually useful. I will say now what I mean by that. So you see, at the moment, what we have is a line bundle on Z, but we actually like to have a line bundle on Y, on the original base, right? So that's what we like to have. But as you can see, there's no map that you can use to pull back a line bundle from Z to Y. So we don't have that. So the question is, okay, how do we lift this line bundle that we constructed from Z to Y? And so basically what happens is with this sort of new construction, what you can get relatively easily and naturally is functorial properties for this construction of this line bundle. So in a sense, the construction of this line bundle that we have is in some sense functorial, and you can use these functorial properties to lift this line bundle from Z to Y. So in this step, kind of depending on what method that you've used, you have to do different amount of work probably. But yeah, so this is all I wanted to say, that you know, constructing this line bundle on Z is not the end of the story. Okay, so now that we have this sort of general idea of what I mean by importance of this model of functors in the non-archer-trivial case, let me give you some ideas about. Okay, so maybe I should make this precise. So this is the theorem that I was talking about. So you know, at the end, if you have these functorial properties, you can actually construct a line bundle on Y. So this is the end result. This should be the end goal, which one can do once you have this functorial stuff. But what I haven't talked about is actually how you construct this line bundle L, because this is probably sort of very important part of all of these things, that how you construct such line bundles, positive line bundles, you know, birationally. So I will just talk about the main sort of key points behind the construction of such a thing. And I'll start with, so in this theory, the starting point is always positivity of direct images. So for simplicity, so I'm not actually going to give you all the details. I'm just going to give you the general idea. So I'll make some assumptions and I will be vague sometimes. So for starters, I will just make the extra assumptions that this sort of compactification is semi-stable. That will help with a few things. So let's just make that assumption for simplicity. And let's start with always the first step, that you know, this variation, the first thing that one can conclude out of existence of variation in the family is positivity of direct image sheaves, determinant of direct image sheaves. So what do I mean by this? This is what I mean. I mean that for non-archer trivial families, a Quadratic dimension of a determinant of push forward of this thing. So I'm also reflexivizing, but I'm not saying anything. But basically, this is after reflexivization, I get a line bundle, and then Quadratic dimension of that line bundle has a lower bound in terms of variation. So for some sufficiently large M. So this is always the first step. Sort of how variation is sort of translated into a birational positivity property like that. Okay, so now in practice, at least in the context of this problem, one needs a slightly better positivity result in the following sense. So from this, one can conclude that there is a line bundle L whose Quadratic dimension is what we like it to be. It's bounded from below by variation, and such that we have this strong positivity that the relative canonical twisted with pullback of dual is M power has global sections. So, okay, so this is a place that I'm being a little bit vague, because this sort of positivity is actually not true on the original family. This is only true after you replace the original family by a large public product. So this is why you know, the implication is not completely as of written. So I've already replaced X by something much larger. But after you do that, you have this strong positivity result, and this line bundle is extremely useful in what's going to happen next. So I'm going to give it a name M. Okay, so now that we have a positivity in this sense, now let's see there's always a next step. And the next step has to do with basically controlling the Hodge theoretic algebraic properties of this family in the boundary. So that, you know, when we talk about variation of Hodge structures, and you want to know what happens, you know, at the boundary of variation of Hodge structures, you have this various sources of extensions. And the most important one is the Leans canonical extension. And actually that will serve as sort of the basis of how things will work out, how we will construct, how we will sort of turn the positivity that we have in this step to positivity inside the Shikopuri differential forms. So I'm going to sort of talk about that a little. To construct these canonical extensions of variation point structures, one looks at, or at least for Deligne, one looks at log differential forms and relative log differential forms. So the log differential forms of fixed degree come with some natural choice of filtration. So these are so-called, sometimes are referred to Koszul filtration. So these are decreasing filtration with this property. So, and basically these filtrations are the key to constructing, basically, if you like, to constructing the homomorphic part of Gauss-Bonnet connections. And we actually, the way these things will appear is in a similar way. So the fact that these filtrations sort of control how sort of Higgs fields underlying variation point structures behave and how they behave in the boundary will be essential for us in this sort of story as well. So let me say what do I mean by this? So what we are going to do, we are going to look at basically the first step of filtration. So let's consider the first step of filtration for 0, and that will give me an exact sequence like that. And then kill the second step. So I'm going to replace this by GR1. Now I have a sort of short exact sequence like that. And as I said, this is the short exact sequence that pretty much controls the Higgs fields for variation point structures if you do something like the following. So what we are going to do, we're going to consider a twist of this short exact sequence by this line bundle that we found in step 1, M, its dual, and then apply this derived functor push forward to the resulting short exact sequence to find maps. So if you do that, then you get connecting maps in the long exact sequence that you get to find maps like that. So R push forward GR0 M-1 maps to RI1, I plus 1, push forward GR1 twisted with M-1. So these are the maps that you get from the long exact sequence that arises after you sort of apply this derived functor. Yeah. So now I'm going to look at this. So let me fix something. Let's say N is the relative dimension. And let me fix, so let's fix P to be N minus I. So I'm going to look at sort of special parts and special pieces of these maps. Yeah. So I'm going to sort of look at these maps for a particular choice of P. If I do that, then what I get is these shapes. So I get relative log differential form twisted with M-1. And then this maps to, I'm just using the definition of GR1 here. Twisted with Ri plus 1, push forward. So this will be messy. So maybe it's better to do it here. Okay, so this looks a little messy, but let me just simplify this by assigning some notation to the whole thing. So let me call this Fi. Then what we're having is we're sort of constructing, so we can use this to construct a system. So use this to construct the system. It's kind of an ad hoc system that we're constructing out of these sheaves and out of these maps. And by system, I mean we have a graded structure like this, and we have maps that sends each piece to the next one like this, which is pretty much exactly, this is, if you had a various Hodge structures, the underlying system of a Hodge bundle, the underlying Higgs bundle, it looks exactly like that. So this is why I mean that this sort of Birational Hodge structures and the maps that you get between different pieces there are really the inspiration for how this stuff works. Okay, so now the obvious question is, okay, what is the point of doing all this? What is the point of constructing this ad hoc system like that? So let me say what the point is. So what is the point? Okay, the point is this massive trick. So there's fantastic trick here, and this trick, by the way, so goes back to Kovacs and Behrouz. So this is the trick. This is a great trick. So F0. Let's see what F0 is. So F0 is the sort of first non-zero non-zero weighted piece of that ad hoc system that I've constructed. So F0 by definition looks like this. Right, and I've assumed that the family is semi-stable, so the two sort of log canonicals cancel out, and I get L. So F0 is isomorphic to L. Okay, so that's good, because L, by the way, is the line bundle that carries this right positivity as the right codar dimension, if you like. Okay, so how do I use that? Well, I can apply this tau to F0 to get a map to here, and then I can keep doing this. So I can keep doing this to go to another, to the next one. And again, I can keep doing this. To get maps like this. Okay, so again, what's the point of doing that? Especially because this is a bit suspicious, because this could be useless if the first map is 0. I mean, if the first map is 0, we're not getting anything out of this. So how do we know this has any use? Well, let's make an assumption. So I'm going to make an assumption. I'm going to make an assumption that will exclude that possibility. So assume, so let me just say that assume that kernel of the restriction of these maps to each graded piece, which I'm going to call Ni, is negative. So I'm going to make this assumption that this is semi-negatively curved, if you like, semi-negatively curved. So analytically, what this means is that basically you have a sort of a metric with a semi-negative curvature current. But algebraically, this means that this is the same as weak negativity, or its dual is weakly positive. So this is weakly negative. Or its dual is weakly positive. And weak positivity is basically a generalization of pseudo-effectivity for higher rank bundles. So if you know what pseudo-effectivity is, a similar notion can be sort of crafted for higher rank bundles, and that's weak positivity. Now, what is this good for? Well, if the kernel of these maps is negative, then there's no way that tau, the first tau, can kill L, because L has global sections, right? So L is that good line bundle. L has the right codar dimension. It particularly has global sections. So it cannot be killed by tau, because anything in tau is negative. So that means that we can sort of keep applying tau. So that means tau, this line bundle L goes through these maps without being killed at the first step. So the trick is, this is a trick. So this is why this trick is good, is that once you have this assumption, then there exists a natural number k bigger than 1, such that L maps to, so this bundle maps to the kernel of this maps times the sheaf of log pre-differential forms. So you see, we are getting close. We are getting close to tracing a connection between this line bundle and pre-log differential forms. The only annoying part is this kernel nk. But the thing is, we know something about that. Well, we made an assumption that it's negative. That means that I can use that to form this injection inside the sheaf of log pre-differential forms for large enough m. And so I know nk, this sheaf is negative, if you like. So its dual is positive in the sense that this is pseudo-effective. So this is a pseudo-effective line bundle. So up to a twist, up to a twist of pseudo-effective line bundle, I've now managed to inject this line bundle with the right quadratic dimension inside the sheaf of log pre-differential forms. Now you see, so before I go further and I explain why this assumption makes sense, let me just say that, of course, if we are in the maximum variation case, this is exactly what we want. If we are in the maximum variation case, I said that quadratic dimension L has a lower bound in terms of variation. So in the maximum variation case, L is big. But then if you twist something big with something pseudo-effective, you again get something big. So you get exactly injection of the line bundle with the right quadratic dimension inside the right sheaf. So that's why the maximum variation case basically follows exactly from this sort of injection. So now let me just say why this assumption of negativity for kernels makes sense. Well, it makes sense if you remember something about variation of Hart structures. This sort of assumption is true if this system was the underlying system of variational Hart structures, and that's because of the Griffiths result, and so basically combination of Griffiths result and Catoni-Kaplan-Schmidt estimates of degeneration of Hart metrics, and finally Zhu's result says that kernel of Higgs fields underlying variational Hart structures exactly verify this condition. They are semi-negatively curved. So this means that if we can, you see, we have constructed a system that we do not know if it has a relation to variational Hart structures, but if it did, then this sort of assumption would have been natural. So that's the point. But the thing is, as you saw from the very beginning, the way that system was constructed was very close to how you constructed sort of Higgs fields for variational Hart structures. This is exactly the sort of thing that happens. That sort of construction is exactly the sort of construction that you have for variational Hart structures. The difference is that twist M. So somehow one has to sort of play around with that twist M to see if you can sort of still make a connection between that ad hoc system F and variational Hart structures. And this is what one can do. Yeah. So this is, so I should say that we can guarantee that the assumption holds by finding a connection between that ad hoc system that we constructed with a twist of M and the linear canonical extension of variational Hart structures somewhere. So I'm just going to call it E theta. And this is the linear, so I should make this clear that this is not sort of the linear extension of variational Hart structures of the original family. This is sort of extension of a VHS after you do a cyclic covering. So I should say this is on the cyclic covering associated to the positivity. You see, we said that m to the power m, this thing has global sections. Using that, you can construct cyclic covering. And that E theta that I've written there has to do with the linear extension on that cyclic covering, if, after resolution, if it's necessary. So let me just say, write what I said mathematically. So fact is, there's a map of systems that sends f tau that we constructed to e theta. And I'm going to, if we can look at the image of this map, which is a subsystem of e theta. And the point is at level 0, so phi 0 is injective. So that's key, because phi 0, so that sort of this thing is isomorphic to L. So this is the piece that contains the information about the line model that we like. So in this map, you know, we don't want this to be killed. So we want this to survive, because now on the image of this ad hoc system on G theta, we have the negativity of kernel, because this is a subsystem of extended variational structures. And such things do have, because sort of the, so this theta is the Higgs field, because the Higgs fields are compatible. The kernel of one lies in the kernel of the other, and the kernel of these things are do exactly verify that sort of negativity assumption that I said. So now you run the trick for G basically. So now we can apply the trick, the above trick, the trick above for this image to G theta to get what we wanted. So I'm just going to say L twisted with pseudo-effective line bundle maps to Schiffer-Poolog differential forms. So yeah, so that's sort of the general idea of how these things work. But so if we just follow this, what we have here, so what this shows is that this is always true. So whenever we have a non-trivial family of manifolds of this type, then there's, you know, up to twist of this pseudo-effective line bundle. So I'm calling this pseudo-effective line bundle, I'm calling it beta or B. After this twist, then we have the injection inside the Schiffer-Poolog differential forms. And note that the line bundle is exactly the good one. So it has a right Polar dimension. Now, without knowing anything, you see, so this result has nothing to do. So I didn't say anything about modular functors. So without using anything about modular functors, we always have this. So you always have this. Now, if we combine this result with the following Birational result. So let me say this. So if you have a log smooth pair and pseudo-effective line model and a line model L such that their twist, so they look like what you see up there, their twist injects inside the Schiffer-Poolog differential forms, then assuming that the dimension is at most 5, then we always have this bound. So quadratic dimension of L is always upper bounded by log quadratic dimension of the pair. So you see, again, without using anything about model functors, their existence or anything, we can immediately, so this immediately shows that Kaveh-Kovacs conjecture is true with the assumption that the basis has at most dimension 5, right? Because quadratic dimension of this line bundle is lower bounded by variation. So variation is lower bound for that. And this is upper bounded by log quadratic dimension. And that's exactly what Kaveh-Kovacs conjecture asks for, that the log quadratic dimension is an upper bound with variation. So without using anything about, as I said, modular spaces, you can sort of have this result. This is not immediate and this needs some work, but you can have this result up to dimension 5. And this is actually where construction and existence of these model functors come into the picture. Because once you have that, then you can improve these results. So let me just say that. So by using this pseudo model functor, basically you can, first of all, remove this twist of pseudo-effective line bundle. Yeah, so that's the first thing that we can do, that you don't basically need to worry about this twist of pseudo-effective line bundle. You have the injection of the line bundle with the right amount of global sections, if you like, inside the Schiffer-Poolog differential forms. So that's the advantage of working with modular functors. And as I said, the reason, basically, at least vaguely, the reason that this error term, this error B pseudo-effective line model goes away is that if you sort of construct these sheaves, if you construct this L at the level of modular stacks, where variation is maximal, then you'll be twisting a big line bundle with a pseudo-effective one. So in a sense, the pseudo-effective one doesn't matter, because the twist will still be big. So at the end, you will still end up with a twist, with the injection of the line bundle with the right codar dimension. So this is why this error term, if you like, the pseudo-effective line bundle B goes away if you use moduli functions and moduli spaces. And we can even do more. So there's more to this. There's not just removing of this twist using moduli spaces. There's more. You can actually be very precise about what is the codar dimension of this line bundle that you construct on the base. And that's this. So this is the key. So this is important. So what this thing is saying is, in the non-isotrivial family case, not only we can construct a sort of a line model inside the sheaf of log differential forms. Actually, that line model looks exactly like this. So the line model is inside the sheaf of exterior forms, and its codar dimension exactly matches the degree of these forms. So this is much more precise information, and this really helps with solving Kevers-Kovács conjecture. So actually, also at this point, I can say something about components conjecture, because you see, if you're familiar with the notion of special variety, so component has the notion of special variety. If you're familiar with that notion, what this theorem, this last theorem is saying is that if you have a variation in your family, the base cannot be special. So if you like, specialness is defined as sort of opposite of what's happening here. So a variety is special if all line bundles inside the sheaf of exterior forms with poles, with log poles, has a codar dimension strictly smaller than the degree. Yeah. So here we have a line bundle whose codar dimension matches the degree. So this is exactly a situation where this pair is not special. So in other words, if I want to sort of rephrase what's happening in this theorem, we can say it like that if you want to use the language of this special notion. What's happening is, over special varieties, all families of this form are isotrivial. So this is what this theorem is saying, that sort of, if the base is special, all such families, all families of projective manifolds with Goodwin models are isotrivial. And this means that this is a birational sense. So we know what it means. It means the variation in the family is zero in the sense that we discussed earlier. Okay, so maybe I can also sort of finish by going back to the original conjecture of Shafarevich. You see, the original conjecture of Shafarevich said that, over these curves, CC star P1 and elliptic curve, the families of homogeneous curves are isotrivial. And actually, these curves are the full list of all special curves. So in a way, what we just did was generalization of this. So if Shafarevich says that families of homogeneous curves over special curve are isotrivial, this theorem is saying that families of projective manifolds with Goodman models over special base are always isotrivial. So the base can be on any dimension, of any dimension, and if it is special, then the families are isotrivial. And Kevers-Kovács conjecture follows from this. So Kevers-Kovács conjecture follows from this theorem, which basically, as I said, is sort of a solution of a conjecture component. Okay, so let me just, in the past, I can just finish by saying that so there are many names that I didn't refer to properly. There are many people that have been working on this for some time. So at the end, I've just listed, I'm just giving you a list of some of the key results in this area in the past many years, 40 years, 40, 50 years. Of course, this list is not exhaustive, but I'm just saying that if you're interested in having summary of key results here, I'll giving you, there's a list here. And in case you want to know the specific references, you can always email me if you can't find them. Okay, well, thank you very much for listening.
Okay. So thank you. There's any questions? Don't forget to unmute yourself.
Hey, so Behrouz, oh, can you hear me? Yeah. So I wasn't able to, oh, hang on. Dimension 5, you probably said, but some of your results held with the base up to dimension 5 and then some that disappeared.
Yeah, this result, you see, this theorem has nothing to do with boundaries or anything. In general, if you have a pair, log smooth pair, and if you have a twist of line bundles like that, L and a pseudo-vector like that inject inside the sheaf of log pre-differential forms, you can always bound the codaric dimension of the sort of log canonical. This codaric dimension of L forms a lower bound for the codaric dimension of the log canonical. Basically, this is what it's saying. And actually, this should be true in all dimensions. I've used abundance results in lower dimensions. That's why there's a restriction on dimension here. So if you believe that abundance conjecture is true, then this is true in all dimensions. And actually, you do not need to know anything about modular functors to resolve Quebec-Kovács conjecture. Maybe I can also add that if you simplify this, for example, say that boundary is 0, and you have Kerr-Einstein metric, then this inequality is always true. So this is exactly the Buckner inequality.
Okay. Any other questions? Okay, so if not, we'll thank Behrouz again.
Thank you.
You.
And don't forget to stop the recording.
Right.
Stop, not don't pause, just stop.
Stop it, yeah.
And okay.